Night chemistry. Chemical wonder of H₂O. Welcome to night chemistry, your quiet laboratory by the moonlit sea. A gentle surf rolls in and out at 60 beats per minute, matching the rhythm of your heart. Tonight we begin the playlist famous compounds and substances with the most familiar molecule on Earth and perhaps the most extraordinary. Water. 2 hydrogen atoms embrace 1 oxygen atom, and from that simple pattern arises clouds and glaciers, rivers and blood, the storms of Jupiter and the breath inside your lungs. In the next hour we will drift through water's chemical secrets. We will visit candlelit Parisian laboratories, trace isotopes frozen deep beneath Antarctica, and watch electric sparks pull water apart only to let it fuse again in silent power. While the science unfolds, a steady tide of calm will carry you towards sleep. Leave behind the noise of the day. Let the shoreline darken, the stars brighten, and the hush of curiosity settle over you like a warm blanket. Our journey begins now. Settling into water calm. Find a comfortable position, seated or lying down, where your spine feels long and unburdened. Allow your shoulders to soften as though they are melting into warm sand. Gently close your eyes or lower your gaze. Notice the cool night air touching the tip of your nose. Tidal breathing. 1. Inhale through the nose to a steady count of 4. 1, 2, 3, 4. Lifting the breath as if drawing a clear spring up from the earth. 2. Hold that breath for 4, secure and buoyant, feeling a quiet ripple spread from chest to fingertips. 3. Exhale for 6. 1, 2, 3, 4, 5, 6. Letting the day flow out like a river meeting the sea. Repeat this cycle 2 more times at your own pace. With every exhale, imagine a circle of ripples widening across a still pond, carrying away tension in perfect rings. Hear distant waves folding onto the shore, each crest dissolving into gentle hiss. Taste a hint of salt on your lips. Smell petrichor, the earthy perfume that rises when rain touches dry ground. Now picture a single droplet of water suspended before you. Its curved surface reflects the Milky Way in miniature. Rotate the droplet in your mind. See how it captures light, how its surface trembles with unseen energy. Within that tiny sphere dwells every story we are about to tell. The spark of Cavendish, the naming hand of Lavoisier, hidden isotopes, and the silent dance of protons that never truly rest. Let the droplet grow until you are floating inside it, weightless, surrounded by shimmering blue. The outside world fades. Only the soft pulse of water remains, a universal heartbeat echoing through oceans, clouds, and the blood that moves quietly beneath your skin. Take one final tidal breath. In for 4, hold for 4, out for 6. Feel yourself buoyed by the simple grace of H₂O. When the next breath arrives, you will be ready to explore its chemical wonder. From myths to molecules, the night sky above the shoreline is clear enough to show every star, yet long before constellations were charted, people imagined a darker ocean cradling the world itself. In Sumer, that cosmic sea was Tiamat, a goddess so vast that gods were said to carve rivers from her body. Across the Mediterranean, Greek philosophers folded water into their own origin tales. Thales of Miletus declared it the first principle of all matter. Aristotle ranked it among his 4 unbreakable elements, cool and moist, forever cycling through clouds, rain and dew. Centuries slipped by. Alchemists collected morning condensate on silver bowls, calling it aqua celestis and praising its power to dissolve the rigid and revive the dead. But their furnaces and retorts never separated the liquid into anything simpler, so the conviction endured. Water was elemental, indivisible, eternal. Everything changed in the summer of 1781, when Henry Cavendish, shy, reclusive, known to file his coins by chemical symbol, sealed 2 invisible airs inside a glass globe. One he had painstakingly extracted from sulfuric acid on iron, the other he drew from the very atmosphere. A tiny spark bridged the gases, and with a sharp pop the interior misted over. Cavendish cooled the globe, weighed it, then weighed it again after absorbing the moisture. Mass had shifted in perfect balance. Something profound had happened. Two colorless gases had vanished, replaced by liquid water. The experiment whispered a forbidden idea. Perhaps the ancient element was not an element at all. Across the channel, the whisper became a trumpet call. Antoine Lavoisier repeated Cavendish's combustion with the precision of a tax auditor. His previous occupation, tracking each milligram entering and leaving the apparatus. To the heavier gas he granted a new name, oxygen, acid former. To the lighter, hydrogen, water former. Arrange them in a 2-to-1 embrace. He proclaimed, and O appears. In a single paper Lavoisier decapitated phlogiston theory, redrew the language of chemistry, and proved that water could be written as an equation. 2H2 plus 2H₂O. Imagine his laboratory in the arsenal of Paris. Glass bell jars reflecting candle flame, mercury sliding through U-tubes, the faint scent of potash in the air. On a mahogany table sits a fresh bead of water, invisible to the casual passer, but yet massive enough to topple 2,000 years of thought. Even so, the story was incomplete. Chemists knew the parts and the whole, but not the shape that held them together. Many early diagrams sketched water as a simple line. H₂O, perfectly straight. Only with the rise of quantum mechanics in the 1930s did spectroscopy reveal a subtle bend, 104.5 degrees between the hydrogens. That tilt, so slight on paper, grants the molecule a split personality. One side faintly positive, the other faintly negative. Billions flock together like tiny compass needles, weaving a lattice of hydrogen bonds that forms, breaks, and reforms 1 trillion times a second. Those clandestine bonds explain why insects can skate on ponds, why ice floats, why oceans remember yesterday's sunshine and release it to soften winter nights. Yet hydrogen bonds are generous in more than comfort. They open secret passageways for protons to hop along chains of molecules, a quantum relay race called the Grotthuss mechanism. A single proton can migrate through liquid water at reckless speed, a vital shortcut for the pulses inside your nerves and the acid-base chemistry of life itself. Less than half a century after Lavoisier's naming, electricity offered a new knife to slice the droplet. In 1800, physicians William Nicholson and Anthony Carlisle wired Alessandro Volta's newly invented battery to river water tinged with a bit of acid. Bubbles blossomed on opposing copper poles, hydrogen at one, oxygen at the other, like twin strings of silvery pearls. Electrolysis not only confirmed the water formula but hinted at an even grander symmetry. If fire could unite gases into water, perhaps invisible currents could separate water back into its parents, or drive machines with pure hydrogen flame too clean to stain a teacup. Chemical curiosity, however, is never content with the ordinary isotope. In 1931, the American chemist Harold Urey chilled tons of liquid hydrogen and discovered a heavier twin, deuterium. Bond two of those heavy hydrogens to oxygen and the result is heavy water, D2O. Slightly sweeter on the tongue, freezing at 3.8 degrees Celsius, boiling at 101.4 degrees Celsius, and invaluable for taming neutrons inside a reactor core. In the Second World War, Norwegian commandos risked their lives to sabotage a hydroelectric plant that piped D2O to Nazi laboratories. Trace amounts of that same liquid now shield critical isotopes in cancer therapy and power peaceful CANDU reactors that illuminate winter nights without a puff of carbon. Even oxygen carries isotopic secrets. A rarer sibling, O18, sneaks into snowflakes more readily at higher temperatures. Locked in Antarctic ice sheets, its ratio to common O16 forms a frozen diary of 500,000 years of climate swings. Glacial advance, Sahara monsoons, volcanic winters. To melt an ancient core and analyze a droplet is to read yesterday's weather on a continent that has not seen rain in millennia. Some wonders hide in plain water. At any given moment, 2 of every 10 million molecules spontaneously tear apart. One donates a proton, the other accepts, creating hydronium and hydroxide in a flicker too fast for sight. This autoionization gives water its neutral pH 7 baseline and prepares the stage for every acid or alkali that follows. Heat the liquid near a deep-sea vent, 250 degrees Celsius under crushing pressure, and neutrality shifts. What seems caustic in your teacup becomes gentle in the abyss, shaping alien ecosystems of tube worms and chemoautotrophic microbes that feast on the chemistry of the Earth's mantle. Push harder, 374 degrees Celsius and 218 bar, and the droplet abandons its surface altogether, slipping into a supercritical state that is neither liquid nor gas. In that ghostly realm, a feather of organic grease dissolves as readily as salt. Engineers now dream of supercritical water reactors that could burn nuclear waste into shorter-lived ash, while planetary scientists suspect similar oceans lurk beneath the clouds of Neptune, hotter than a blast furnace yet denser than lead. Lift your gaze once more to the real ocean under starlight. Each wave crest curling toward the beach is built from the same bent molecules Lavoisier weighed and Cavendish coaxed from flame. Every shard of moonlight the water reflects has bounced off hydrogen bonds strong enough to make mountains of ice yet fragile enough to snap in a picosecond. Those crests will evaporate by dawn, rise into clouds, and perhaps fall again next year on another continent, entering the sap of a cedar or the bloodstream of a deer. Take a slow breath. The air filling your chest is humid with trillions of former raindrops, some exhaled by ancient astronomers, others lifted today from equatorial forests. Within minutes, a few stray molecules from Henry Cavendish's laboratory may pass through your alveoli and slip, unseen but not unfelt, into your blood. Water remembers nothing, yet it touches everything. Its chemical story is at once humble and cosmic, grounded in glassware and spread across interstellar clouds where infrared telescopes map vapor swirling around infant suns. 2 hydrogens and 1 oxygen. A formula brief enough to fit on a thumbnail, powerful enough to sculpt continents, cradle embryos, and keep the delicate engines of thought humming as you listen, eyes closed in the dark. Allow the scene to linger. Candle flames flicker out in 18th century Paris. Tesla coils sputter in Victorian lecture halls. Polar snow settles in muffled silence. And somewhere, inside a cell in your heart, a hydrogen bond breaks and reforms, timing the beat that guides tonight's tide of rest. Inhale gently, hold, exhale longer. The laboratory door closes. The droplet returns to stillness. When next you breathe, we will slide deeper into the marvels that physics, ice, steam, and the dancing lattice between, has yet to reveal. The grammar of a bent molecule. Picture the single droplet once more, floating against the dark. Zoom in until the atoms themselves stand before you like bright lanterns. At the center glows oxygen, heavier and greedier for electrons. On either side, 2 lighter hydrogens sway like dancers holding out their arms. They do not line up in a straight row. Instead they meet at a shallow V-shape, an angle of 104.5 degrees. That modest bend turns the entire molecule into a tiny magnet. The oxygen end carries a hint of negative charge. The hydrogens share a gentle positive blush. Every droplet of water is therefore a compass needle in miniature, forever seeking company. Now imagine an ocean of those needles. Each positive tip yearns for the negative waste of a neighbor, forming what chemists call a hydrogen bond. A handshake too quick for sight yet strong enough to lace billions of molecules into a restless net. These bonds break and reform in less than a trillionth of a second. Their ceaseless shuffle grants water 3 miracles the planet depends on. First, surface tension. Run a fingertip across a still pond at dusk. The skin of the water pushes back like silk stretched on a frame. Pond skaters tap dance on that tension. Ink droplets in a calligrapher's dish hold a perfect dome. Each tear that slips down a cheek beads for a heartbeat before it falls. Only mercury grips itself more tightly. And mercury is far denser and far rarer. Water achieves this with nothing but hydrogen bonds. Invisible threads drawn tight over every ripple. Second, an odd quirk of density. Most liquids grow steadily heavier as they chill. but water sinks only until it cools to about 4 degrees Celsius. Below that, the lattice of bonds begins to open like a blossoming crystal, pushing molecules farther apart. Ice is therefore lighter than the liquid beneath it and floats, an upside-down arrangement that insulates rivers in winter and keeps fish alive beneath a glassy ceiling. If frozen water were heavier than its melt, every lake on Earth would fill with solid ice from the bottom up and thaw only at the rim. Life as we know it could not have survived the first deep freeze. Third, an enormous heat bank. Because those bonds must be broken to raise the temperature even a little, water can absorb oceans of energy without growing hot in a hurry. That generosity smooths day-night swings, carries warm currents across entire hemispheres, and stores summer sunlight inside the great blue reservoirs that ring the continents. Walk along a beach at night, feel the air warmer by a few degrees than inland, and you are standing next to the planet's memory foam. Yet the grammar of water grows stranger the closer we look. Drop a dye crystal into a glass and the color spreads, not only by slow diffusion but also through microscopic rivers called molecular streams, guided by the push and pull of uneven charges. Place a glass capillary into the same water and liquid will crawl upward against gravity, clinging to the walls because the attraction between water and glass is stronger than water's attraction to itself. Trees depend on this capillary rise. So do ink pens and porous pottery and the fine veins in a human lung. Tilt the scene toward the cold, and the bonds arrange themselves into more than one kind of ice. Besides the familiar snowflake lattice, there is cubic ice that forms in high clouds, needle ice that grows like hair from wet ground at dawn, and at least a dozen exotic phases coaxed into being only under crushing pressure, stacked, distorted, or folded arrangements that could tile the floors of alien planets. Scientists have numbered them like rare postage stamps. Ice 2, Ice 3, Ice 16 and onward. Each holds its molecules at new angles. Each refracts light in its own subtle hue of blue. Turn instead toward heat and pressure, and water slips past the line that separates liquid from gas. In this supercritical state it becomes ghostly. No surface, no distinction, able to flow like steam yet dissolve oils like alcohol. Engineers dream of using such water to wash pollutants out of soil or coax stubborn plant fibers into biofuel. Inside giant planets, supercritical oceans may churn beneath clouds striped with lightning, forging storms that last a century. Between frost and flame lies the gentle realm of the body. Here hydrogen bonds choreograph life itself. They zipper together the spirals of DNA, fold enzymes into precise origami, and let protons leapfrog through chains of molecules at lightning speed, fueling the spark inside every nerve. With a bond a little weaker, proteins would unravel, a little stronger, and metabolism would stall. Almost everything alive balances on the thin edge of that energy, as though evolution tuned water's handshake to fit the music of cells. Pause for a breath, a slow inhale for 4 counts, a soft hold, a long exhale for 6. Feel the same choreography inside your bloodstream. Plasma cradling red cells, each red cell carrying oxygen that once glided through liquid caves inside a leaf. The grammar of the droplet links rain to maple syrup, glaciers to whale song, exhaled vapor to the northern lights, all through a bent angle and a playful bond measured in 20 trillion times per second heartbeats. Let the thought settle like silt at the bottom of a pool. The next time moonlight trembles across a glass of water, you will see not just a clear liquid but an epic written in hydrogen bonds. Chapters on surface tension, density, heat, capillarity, and crystalline poetry. Every clause depending on that one modest bend between 2 light atoms and 1 dark companion. Exhale fully, releasing any remaining tension. The droplet grows quiet again, ready to share deeper secrets. Secrets of heavy twins and isotopic footprints frozen in ancient ice. When you are ready, we will drift onward. Heavy Twins and Frozen Diaries. A pale winter evening hangs over New York in 1931. Inside a basement laboratory at Columbia University, Harold Urey watches liquid hydrogen boil like ghostly milk in tall silver flasks. Drop by drop, he lets the vapor condense in a glass finger cooled with liquid air. Hours pass. The men in wool coats stamp their feet to keep warm. At dawn, the finger holds a bead of water that weighs ever so slightly more than expected. Within that extra weight lies a secret. Some hydrogen atoms carry not one particle in the nucleus, but two. Urey names the heavier form deuterium, from the Greek word for second. Bond two of these heavier hydrogens to oxygen, and the result is heavy water. It pours almost the same, tastes faintly sweet, and freezes a little above the familiar zero. Set a cube of heavy ice into ordinary water and it sinks like crystal glass, proof that density can flip with a single neutron. Chemists soon discover that heavy water is a gentle street lamp for neutrons, slowing them so they linger inside a nuclear heart. That kindness turns out to be priceless, both for peaceful power and for darker dreams. Shift the scene to a Norwegian plateau shrouded in February snow. The Vemork plant hums above an icy gorge, its turbines fed by waterfalls. Barrels of heavy water roll down conveyor belts bound for wartime Germany, where physicists hope to coax uranium into a weapon. Under the long night sky, a small band of commandos skis through spruce and silence. They carry nothing but explosives and a promise. Keep the heavy water from ever reaching Berlin. They climb a frozen cliff, slip through a cable tunnel, and set their charges among the barrels. When dawn breaks, liquid miracles drain into the canyon, lost to the river. The saboteurs vanish into the blizzard, leaving history to choose another path. After the war, heavy water returns to quieter work. In Canada, engineers build Canada reactors that use it as a moderator, allowing ordinary uranium to fission without enrichment. In hospitals, a wisp of deuterated tracer mixed into a patient's drink lets doctors watch the flow of blood or the birth of DNA under a scanning camera. In biology labs, fruit flies raised on heavy water emerge a little slower, their wings beating out of sync, a gentle reminder that even tiny changes in mass can bend the rhythm of life. Hydrogen is not the only element with hidden siblings. Oxygen 18 carries 2 extra neutrons compared with the everyday form, and water molecules that include it behave just differently enough for nature to sort them by temperature. Warm air lifts the heavier drops less eagerly than the light ones. Cold clouds drop them sooner. Year after year, snowflakes record the ratio of heavy to light oxygen the way tree rings record rainfall. Deep in Antarctica, ice cores extend more than 3 kilometers down, layering winters back to 500,000 years. Scientists melt a shard from 70,000 years ago, feed the vapor into a mass spectrometer, and read the signature of ancient summers. How bright the sun felt, how strong the monsoons marched across Africa, how abruptly an ice age surrendered to spring. Hold a cube of that ancient ice between gloved fingers. The air trapped inside is soft with forgotten mammoth breath. Yet the water itself is older still, evaporated from tropical seas, blown across continents, frozen under relentless twilight, waiting for a researcher to unlock its diary. Every ratio of oxygen isotopes sketches a line on a graph. Together the lines become a symphony of climates that guides today's debate about tomorrow's oceans. Isotopes also serve as clocks. A lighter cousin of deuterium called tritium is made by cosmic rays at the top of the atmosphere. It decays like a slow heartbeat, half gone in a little over 12 years. Hydrologists track tritium pulses from mid-century nuclear tests as they seep into aquifers. When a well is tapped, the age of the water tells how fast a valley recharges, whether a city is sipping rain from last decade or from the days of the Silk Road. Closer to home, a teaspoon of water in your glass tonight contains about 20 drops of deuterium, too few to taste yet enough for a physicist to weigh. Those drops drift through oceans, rivers, and clouds exactly as their lighter cousins do, weaving deuterium into every cell of every creature. At this scale, the planet's circulation is a single slow inhale and exhale, cycling heavy and light atoms through glaciers, grapevines, and the quiet chambers of the heart. Inhale gently, noticing the coolness along the nostrils. Somewhere in that breath floats a molecule first condensed in a 19th century coal fire, another chipped from a Viking Age iceberg, another stamped with a heavier grin of deuterium. Exhale, and they rejoin the endless exchange. Heavy water saved by sabotage, oxygen isotopes etched in mile-deep ice, tritium ticking in hidden aquifers. Each story adds a new shade to the portrait of a clear liquid that is never truly simple. And yet the droplet hanging in your mind still looks transparent, still shivers with a faint polarity described in the last chapter, still ready to split with a silent flash of electricity. Let the laboratory lights dim. The bead of heavy water settles into a glass vial, labeled and silent. Snow drifts across the Antarctic plateau. A Geiger counter clicks once in a distant monitoring well, marking the passage of tritium through limestone. All these murmurs fade into the steady hush of nighttime surf. Take a slow breath in, hold, and breathe out a fraction longer. The isotopic tale comes to rest. Ahead lies the spark of electrolysis and the promise that water, once parted, can return as clean fire for the future. Sparks, currents, and the clean fire of tomorrow. Moonlight has risen higher, painting the shoreline with a ribbon of silver. Waves reach, pause, and retreat, each foamy edge a metronome that steadies the heart. Somewhere behind the dunes a lone firefly drifts, pulsing like a tiny laboratory lamp. Allow its faint glow to become the first warm ember of tonight's story, because what follows is a tale of light coaxed into liquid, of silent currents moving through glass tubes, of a clear droplet surrendering its hidden flame and then taking it back again. Gently let your shoulders soften. Ease the muscles behind your eyes. Guide a slow breath inward for 4 counts, cradle it for another 4, and then release for 6. As the air leaves, imagine a trickle of water sliding down polished copper, leaving a slender path of dew. In that glistening path lies the key to a centuries-long quest: how to split water without heat or violence, using only invisible rivers of electricity. The first battery, the first break. It begins on a damp afternoon in Milan during the closing days of the 18th century. Alessandro Volta, tall and reserved, has layered discs of silver and zinc with brine-soaked cloth until the stack resembles a delicate pastry. He calls the device a pile, yet when he presses a wire to its top and another to its base, a shimmering spark leaps forth, gentle yet insistent, like lightning scaled for the study. News of the pile crosses Europe almost as fast as rumor can fly, and within months 2 English physicians, William Nicholson and Anthony Carlisle, decide to test the spark against water itself. They fill a small porcelain cup with river water brightened by a pinch of acid, dip in 2 needle-thin wires, and connect them to Volta's creation. A hush settles over the room. At the tip of one wire, pearly beads collect and drift upward in languid strings. At the other, delicate bells of gas escape toward the surface. They are witnessing the birth of electrolysis. Water quietly releasing its parent gases, one wire pulling free the lighter element that loves to burn, the other lifting the element that lets everything else breathe. Nicholson and Carlisle measure, weigh, and taste the escaping gases, convinced they have caught chemistry performing inside out. What flame usually joins, electricity now divides. The experiment becomes a bonfire of curiosity. The president of the Royal Society writes that a new continent has appeared on the map of science. Volta, far away, smiles at how a stack of dinner plate metals can whisper a secret older than rivers. Pause and notice your own breath rising, floating, and disappearing like those early bubbles. With each inhale, picture faint chords of light threading through a calm pool. With each exhale, see those chords dissolve again into water, waiting to be summoned once more. Faraday draws the blueprint of ion worlds. 2 decades pass. In a lecture theater smelling of varnished oak and whale oil lamps, Michael Faraday stands before a glass vessel shaped like an hourglass. He is modest in manner yet fierce in attention, possessing the rare gift of seeing order in a tangle of wires. Faraday recasts the trick performed by Nicholson and Carlisle with new vocabulary. Where others speak of positive fluid and negative fluid, He introduces the words electrode for the wires, anode for the path of entry, cathode for the exit, cation and anion for the charged travelers. He also discerns a law hidden in plain view. The quantity of gases released is directly proportional to the amount of electric charge that passes. Double the charge, double the yield. It is as if the droplet keeps strict account books, balancing every spark with just the right number of escaped atoms. Faraday's notebooks, preserved in the basement of the Royal Institution, contain page after page of neat handwriting, each line a bridge between invisible worlds. View his laboratory in your mind. Copper coils wound like sleeping serpents, jars half full of tinted solutions, a single candle trembling beneath a broad reflector. Outside, London fog muffles the bell of St. Martin in the Fields, but inside, the silence is electric. Industrial echoes, chlor-alkali and the edge of aluminum. By the middle of the 19th century, factories along the Tyne and the Rhone are humming with brine tanks. Saltwater flows between iron grids, and white crystals of soda ash accumulate at the edges, destined for glassworks and paper mills. The same principle, electricity rearranging ions, will later yield shimmering beads of aluminum, a metal once considered rarer than gold. Engineers drop powdered alumina into molten cryolite and run colossal currents through the bath. Oxygen visits one electrode and departs as invisible gas. Liquid aluminum pools at the other, shining like sunrise trapped in a ladle. Though aluminum comes from or rather than water, its birth cries echo the first Nicholson bubbles, proof that Faraday's ledger still governs every spark across every bath. Take another breath, slow and sure. Sense the warmth along your forearms, a hint of the furnace heat where cryolite boils. Then let that warmth fade into a temperate calm as we return to the clear droplet that began this chain of wonders. Hydrogen in the age of steamships and airships. Hydrogen released by electrolysis soon finds work beyond the laboratory. Inflated into silk balloons, it lifts early explorers above Parisian rooftops. Fed into steamship boilers, it mingles with coal to coax hotter flame from iron grates. Yet its temperament is capricious. Hydrogen is eager to escape through rivets, ready to ignite if sparks greet stray currents of air. The 20th century rises on a column of smoky chimneys, and chemists store hydrogen in steel bottles, always marking them with crimson bands and crosshatches. During the golden age of Zeppelins, passengers sip espresso while crossing the Atlantic suspended beneath silver envelopes filled with a lighter-than-dreams gas. Crews know the risk. Each bolt is wrapped in soft leather to prevent sparks. Each smoking room sits inside a heavily ventilated cage. Disaster eventually claims the Great Hindenburg, and public trust in hydrogen collapses overnight. Yet the story of water's child does not end in fire. A new century, a new leaf. Green hydrogen emerges. Now we stand at a different turning point. Giant wind farms scatter petals of white along coastlines. Solar arrays ripple across deserts like black lakes catching the sun. Their power arrives at noon in surges, whispering to grid operators that storage would be welcome, thank you. Electrolyzers answer the call. Inside a modern electrolyzer stack, thin sheets of platinum or iridium rest against membranes so fine they make parchment seem like burlap. Water slips into microscopic channels etched in polymer. An applied current gently persuades each molecule to part ways. Protons migrate through the membrane while oxygen drifts off through a labyrinth of pores, later rising into the sky or feeding steel furnaces that appreciate its purity. The liberated hydrogen waits under light pressure, ready to spin turbines at sunset or fuel ships when tides fall calm. Some designs now capture light directly, foregoing wires altogether. Researchers at laboratories in Boston, Munich, and Tokyo grow semiconducting leaves, ultra-thin wafers coated with catalysts that sparkle like dragonfly wings. Rest one of these artificial leaves on a pond and sunlight rips protons and electrons apart inside its crystal veins, echoing the ancient trick of green foliage but faster, without sugar or sap. The vision is grand yet simple. Water, sunlight, leaf, and the quiet release of flammable gas, stored not in forests but in gleaming cylinders. Breathe in as though drawing air through the pores of such a leaf. Hold. Breathe out, sending a stream of imagined electrons down silken channels, where they meet protons and reunite in gentle light. Fuel cells. The reunion of elements. If electrolysis is a divorce, then the fuel cell is a wedding performed in reverse. In an Apollo command module streaking toward the moon, astronauts sip chilled water from plastic pouches. That water was never lifted from Earth. It is the byproduct of onboard fuel cells where hydrogen and oxygen embrace once more, forming liquid droplets that drift in capsules of zero gravity. The same embrace provides all electricity for guidance computers and cabin lights. Walk into the 21st century. On highways near Los Angeles, quiet sedans slide by, their only trail a puff of water vapor curling in sunlight. Under their hoods sits a fuel cell stack no bigger than a suitcase. Thin plates of graphite, channels zigzagging like garden mazes, membranes coated in platinum as fine as frost. Hydrogen flows one way, oxygen from ambient air the other. Where they meet across the membrane, electrons detour through an external circuit that spins motors and powers dashboards before reuniting with their proton partners. Wheels turn, music plays, passengers talk, and not a single tailpipe coughs carbon into the morning sky. Engineers envision freight ships leaving Rotterdam without bunker oil, regional jets climbing from Denver with tanks of chilled hydrogen slushing in the wings, cities lighting street lamps on power surplus from midday sun split into gas and then recaptured after dusk. They speak of an energy carrier that weighs almost nothing yet stores clean fire in its bonds. Storing the unruly flame. Hydrogen is still restless. It sneaks through nickel at the size of a ghost, embrittles steel until seams whisper under strain, and requires pressures so high that bottles must be wrapped in webs of carbon fiber. To tame it, chemists teach metals to swallow hydrogen like sponges, forming hydrides that lock gas in crystal cages. Others chill hydrogen into liquid colder than Antarctic midnight, then slip it into double-walled tanks lined with vapor shields. Advances arrive each season. Porous carbons as light as smoke, boron-based solids that trade hydrogen at mild heat, pipelines of high-purity polymer that flex without fracture. Imagine one such pipeline running beneath the ocean you hear tonight, a silent artery carrying hydrogen harvested from offshore wind farms toward distant ports. Submarines the size of rushing trout climb and descend along its length to inspect joints. Faint luminescent squid drift close, drawn by the hum of distant compressors. Above, on storm-swept decks, technicians sip coffee while control screens show lines of green lights, each pulse a heartbeat of water redeployed as fuel. Electrolysis in living leaves. Long before Nicholson's wires or Faraday's lecture, nature solved water splitting inside ordinary leaves. The oxygen we breathe each minute rises from manganese and calcium atoms nestled in protein clusters no wider than a virus. Sunlight slaps those atoms with photon after photon until they grow impatient, tugging electrons away from water and flinging oxygen outward like paper lanterns. Protons flow into a reservoir where they help drive the rotary turbines of photosynthesis. Without that gentle theft, animals would choke for breath and mountains would crumble under endless rust. Scientists now map those clusters with X-ray pulses measured in quadrillionths of a second. Each photograph reveals a swirl of atoms frozen midway through the split. By copying those twists in synthetic catalysts, they hope to build devices that store the sun's excess glare inside bonds as sturdy as ancient stone yet as clean as dew. Inhale and picture a chlorophyll molecule unfolding like a parasol, its magnesium heart catching green light. Exhale, releasing the thought that every apple, every cedar plank, every cotton shirt owes its fabric to water torn apart by leaves and sewn back together in a shell of sweet sugar. Lights down, sparks silent. Listeners often wonder why water yields such hidden fire. The answer rests in the dance of electrons. but the droplet itself seems content to hold its peace. When the current stops, gases mingle once more, bonds reform, and heat of fusion drifts out as the faintest warmth, enough to fog a mirror but not to disturb the quiet. The cycle can repeat forever. Divide, unite, divide again. In that eternal rhythm lies the promise that one day engines may spin without thirsting for buried forests, cities may glow without smoky stacks, nights may fall upon oceans undisturbed by oil wakes, and sighs of rest may no longer smell of exhaust but of rain hitting dusty ground. Allow your breath to match that imagined cycle. Draw in cool air, hold it as the electrodes once held charge, and let it go like bubbles rising to meet the night sky. Feel tension unravel from neck to jaw, from jaw to collarbone, from collarbone to the tide of your heartbeat. Sparks dim, currents fade. The dissolving hush returns. Ahead, water will show yet another face. The balanced world of acids and bases, where one shy proton can tip vast solutions from sting to soothe. For now, let the memory of quiet bubbles guide you towards sleep. Copper wires cool. Platinum plates rest. The droplet waits, whole and unharmed, for dawn's first light to glitter across its surface. Acid base wonders in a restless droplet. A hush lies over the shoreline, broken only by waves inhaling and exhaling like some ancient creature asleep beneath the moon. Yet inside every crest, in every spoonful of seawater and every tear, an invisible tug-of-war is unfolding. A contest of protons, so small no microscope can see them, yet so decisive that they shape breath, soil, industry, and thought itself. Tonight we slip beneath the surface of that contest. We will visit coral reefs that change with a single heartbeat of acidity, climb high chimneys where steam vents scald rocks into new colors, and drift through veins and cells where proton pulses keep each heartbeat honest. The scene will stay gentle, calm, suited for night's approach. But behind the calm runs a river of charged possibility. An endless exchange. Hold your palms upward, as if catching a drizzle. Imagine that in the shallow pool your hands now cradle. Two water molecules trade places for the briefest instant. One donates a proton, so light it borders on weightless, and the other receives. In that blink, neither molecule is quite water any longer. One becomes hydronium, bearing an extra hydrogen like a lantern. The other turns into hydroxide, a partner missing its usual companion. Almost before you finish the thought, they trade back again, slipping into the quiet anonymity of the droplet. Chemists assign numbers to this fleeting dance and call the result the water constant. At room temperature, only 2 out of every 10 million molecules carry the temporary lantern of extra charge. Whisper small odds, yet enough for universal balance. Raise the heat, and the lantern exchange quickens. Cool the liquid, and it slows into a kind of dreamy pause. In the abyssal darkness 2 kilometers under the Pacific, where volcanic vents raise water past the boiling point yet pressure holds it liquid, those odds change so much that what we on land call neutral would feel mildly acidic down in that mineral fog. But the vent ecosystems, all tube worms and blind shrimp, are unfazed. Their version of balance simply lives at a different point on the sliding scale. Writing with numbers, speaking with taste. To spare constant fractions, scientists shrink the vast range of proton counts into a neat row of whole numbers. They name the row pH, the letter P followed by H for hydrogen. Each step on that row marks a 10-fold change in proton crowding. 7 sits in the middle as tranquil water at a quiet room. Numbers below 7 describe growing acidity. 6 is the crisp tang of a green apple. 5 belongs to black coffee. 4 to red wine. 3 to chilled orange juice. 2 to the vinegar you splash on salad. 1 to stomach acid digesting supper. Above 7 lie the domain of bases or alkalis. 8 is the silent slip of seawater off a sandbar, 9 the soapy glide of hand wash, 10 the dusty bite of baking soda paste, 11 the slick touch of household ammonia, 12 rises to pipe cleaner, 13 reaches fresh concrete, 14 the far end belongs to laboratory lye that can sculpt glass if left alone. Although the numbers feel tidy, Your tongue knows the truth by sensation. Acidity tingles, constricts, waters the mouth. Alkalinity feels slippery, almost soapy, as if it blurs the fine ridges of the skin. The body recognizes both signals because staying alive means staying close to balance. Blood's secret guardian. Place 2 fingers gently at your wrist or just below the jaw. Find the pulse trotting under skin. Each beat owes its reliability to a chemical bodyguard dissolved in the plasma. The bicarbonate buffer. When muscles burn sugar for motion or the brain burns it for thought, carbon dioxide gas bubbles out of cells and into blood. There it meets water, forming carbonic acid for the briefest heartbeat. Instantly, the bicarbonate buffer absorbs most of the surplus protons, storing them like coins in a vault. If the vault grows crowded, perhaps after a sprint when lungs gasp for more oxygen, breathing speeds up, blowing carbon dioxide out of the chest, emptying the vault and resetting the balance. Should the seesaw tip the opposite way, perhaps after hyperventilation or a prolonged sigh of grief, the kidneys quietly release fewer acidic ions in dawn-colored urine, hoarding them instead to tilt the balance back. All night you sleep unaware, yet chemistry keeps your heartbeat steady within a pH window narrower than the thickness of a hair on the moon. Ocean's breath and corals despair. The global ocean works its own buffering magic, dissolving nearly a quarter of the carbon dioxide humans release each year. At first glance it seems a kindness, yet every borrowed molecule shifts seawater's balance a hair toward acidity. Coral polyps, those tiny architects of limestone cathedrals, rely on carbonate ions, the same coins blood keeps in its vault to build reefs. When acidity rises, carbonate grows scarce, and the living cathedral weakens until storms break it apart. Divers returning to familiar reefs note colors fading, branches dulled and brittle. All from a change so slight a single drop of vinegar swirled into a liter of water could already exceed it. Still, life adapts. Some coral species spawn earlier or later. Some algae cloak the skeletons in helpful biofilms. Some fish graze differently, spreading helpful nutrients. Yet the margin grows thin. Scientists sail in midnight shifts to drop robotic sensors that drift below wave crests, drinking in pH readings like whispered gossip. Data streams homeward, telling a complex story. Pockets of deep water upwelling where acidity is natural, bays where mangroves exhale alkaline plumes, reefs that flourish, reefs that fade. Understanding the chorus allows caretakers to plant resilient coral strains, reroute sewage plumes, or restore coastal grasses that shelter juvenile fish and absorb excess protons. Breathe in slowly as though swelling the chest with tidewater scented by sea grass. Hold that breath, picturing a branching coral glowing under moonlit ripples. Release and send a wave of calm toward reefs still uncharted, waiting for tomorrow's divers. Rain that etched cathedrals. Now lift your mind to high clouds over the industrial age. Coal fires and smelting stacks sent sulfur and nitrogen oxides skyward. Up in the watery haze of clouds, those gases dissolved and formed acids stronger than anything in apple juice or tea. Droplets gathered into marbled rain that fell on forests of spruce and beech, stripping nutrients from thin mountain soils, whitening river stones, wearing gargoyle faces on old cathedrals until their features turned unkind. By the late 20th century, lakes in Scandinavia held water so clear and so empty of buffering minerals that no fish fry survived spring thaw. Children on the shore remarked it looked like bottled water yet yielded no life. Facing that mirror, nations tightened the bolts of scrubbers on smokestacks, refined fuels to carry less sulfur, and within a single generation many lakes recovered enough acidity to invite trout home. A reminder: balance lost can sometimes be found again, if one listens soon enough. From kitchen to laboratory. Think of the kitchen as a friendly chemistry bench. When you knead dough for sourdough bread, lactobacillus bacteria exhale lactic acid, giving the loaf its subtle tang and helping gluten relax so bubbles rise finer. Cheese makers control pH hour by hour, letting rennet cut milk proteins only when acidity slips past a chosen point. Pickle jars harness vinegar's proton wealth to fence out spoilage while letting friendly flavors mature. Meanwhile, lye baths give pretzels their mahogany crust by raising surface pH so high that browning reactions gallop ahead of the oven's heat. Litmus strips, descendants of lichens washed and dried by medieval apothecaries, bleed blue or red at the faintest whiff of imbalance. In school laboratories, the faint blush of phenolphthalein announces the exact moment a solution shifts allegiance from acid to base. Hydrangea blossoms perform a similar drama invisibly. Petals open pink in alkaline soil, blue in acidic, allowing gardeners to change color with a handful of powdered sulfur or crushed limestone. Engines built on proton roads. Inside each of your trillions of cells, tiny bean-shaped mitochondria generate the molecule called ATP, the universal coin of energy. They do so by herding protons across a membrane much smaller than a single pixel on a phone screen. Those protons crowd on one side until they long for release. When they stream back, they spin a rotary motor, driving two molecular paddles together to mint fresh copies of ATP. Every blink, every heartbeat, every synapse that fires while you listen, depends on that hidden motor riding a wave of protons no thicker than fog. Plants, algae, and many bacteria run an almost identical machine in reverse, spending sunlight's credit to haul protons across thylakoid membranes before letting them rustle down again, printing sugar instead of ATP. Thus the same proton traffic fuels animals and builds forests, ties predators to prey, links lungs to leaves. The road is ancient, the toll eternal, a balanced droplet where acids and bases conduct their silent business. Industrial guardians and household helpers. Outside the body, acid-base chemistry runs pulp mills, dye factories, and municipal water plants. When river water looks brown from tannins or smells of algae, engineers blend in a whisper of alkaline lime or acidic aluminum salts, coaxing dissolved particles to combine, settle, and leave the stream bright. In oil refineries, towers dozens of stories tall rely on caustic wash steps that strip sulfurous acid gases before fuel reaches car engines. Without those quiet washes, urban smog would thicken to a sepia haze. At home, many tasks lean on similar balance. Baking soda sprinkled on a grease fire smothers flame partly by neutralizing fatty acids and partly by releasing gentle clouds of carbon dioxide that deny oxygen. A splash of vinegar rinses soap residue from laundry, softening cotton without perfume. Gardeners test soil with color dips. Too acidic and tomatoes struggle. Too alkaline and azalea leaves yellow. Soft corrections with peat or wood ash guide the soil back to harmony. The underworld of extreme acids. Deep inside Earth, water percolates through volcanic rock and meets sulfur gases. There it becomes acid strong enough to dissolve obsidian, carving caves lined with stalactites of native sulfur, a mineral so soft you can mark it with a fingernail. In certain chemical plants, engineers deliberately brew superacids, liquids so eager for protons they strip basic structure from molecules in microseconds. They temper these ferocious reagents with Teflon gaskets and remote-controlled arms, pursuing catalysts that shave energy from fertilizer production or turn crankcase oil into fragrances. One might ask why humans court such extremes, yet in doing so they map the boundaries, knowing better where safe harbor lies. By understanding fury, gentleness grows. Quiet closing balance. Let your breath fall into that pattern again. A slow tide inward, a weightless pause, a gentle tide out. Imagine a beam balance on a jeweler's table. One pan labeled acid, the other base. Grains of silver dust added one by one until the bar levels. That balance exists always inside a spoon of water, a lake, a blood vessel, the blue planet itself. Tiny protons, almost massless, decide the outcome. Picture those protons as pale fireflies flickering between molecules, sometimes clustering, sometimes dispersing. See how a slight lean toward clustering sharpens the flavor of citrus, etches marble, tests coral strength. Watch the lean toward dispersal slick hand soap. Give brine cured olives. Let bee stings fade under a baking soda paste. Everything returns to stillness if allowed. Now guide a final breath through your nose, imagining it passing over litmus that glows lavender, the shade of perfect neutrality. Hold the air in gently, thankful for the buffering vault in your blood that has guarded you since your first gasp at birth. Release the air slowly, as if giving a gift to night-blooming jasmine. Feel shoulders loosen, jaw unclamp, mind quiet. The proton dance continues without supervision. You may set it down like a lantern at the edge of a moonlit pond. Ahead waits the realm of extremes. Supercritical oceans hotter than flame, ice phases harder than granite, yet for the moment balance is enough. Rest in the certainty that a humble droplet knows how to keep its own scales level, and in doing so keeps you, and reefs, and forests, and marble statues company through the slow turning of the planet toward dawn. Beyond ice and steam, water at the edge. Night has settled into its deepest hue, a velvet so dark the Milky Way seems nearer than the dunes. Listen to the hush between waves. A pause long enough to imagine water not as surf or rain or mist, but as a shapeshifter that slips into realms few eyes have seen. Tonight we follow the droplet beyond familiar boundaries. Past boiling, past freezing, past the tidy labels of liquid and vapor, into arenas where pressure crushes, lightning tears, and atoms rearrange themselves into forms that glint like alien jewels. Let the shoreline fade. Let curiosity guide you through extremes where silence and power intertwine like twin currents in the dark. Supercritical ghosts. Begin far offshore, 300 meters beneath the Pacific, where black chimneys vent mineral-rich water as hot as molten glass. Pressure clamps down here with the weight of 200 atmospheres, so the liquid cannot boil even at temperatures that would roar away in an open kettle. Instead it crosses an unseen frontier into the supercritical state, neither liquid nor gas, but something midway, a phantom with no surface tension and a density that can swing from airy to syrupy with a nudge of pressure. Imagine drifting beside a vent. Supercritical water glides through cracks in basalt like warm smoke through lace, dissolving metals that ordinary water would only rinse. When the fluid meets cooler seawater, it flashes into billowing plumes, raining tiny crystals of pyrite that glitter under submersible lights like gold dust in autumn sun. Microbes cling to chimney walls, feasting on chemical energy born of this ghostly solvent. They thrive without sunlight, proof that life may root itself wherever water learns new tricks. Now lift the scene from ocean floor to laboratory. Engineers pump purified water into steel tubes as thick as a sailor's wrist. Heat it beyond 374 degrees Celsius, then use the supercritical stream to strip toxic dyes from clothing waste or break down medical refuse into harmless salts. A pilot reactor outside Kyoto hopes one day to feed supercritical water a steady diet of plastic shards, returning only carbon dioxide and distilled liquid to the air and sea. In another plant, scientists test a new nuclear design that lets fission heat supercritical coolant, promising turbines that capture more energy while leaving fewer radioactive ghosts behind. Everywhere the phantom state goes, old limits soften like wax beneath a flame. Liquid under tension. Shift now to a forest at dawn. Saplings sway, leaves drink light, and inside each towering pine a quieter drama unfolds. Tiny straws of xylem draw water upward, sometimes more than 100 meters against gravity. They do so by pulling, not pushing. Each water column is in tension, stretched like a violin string. The liquid is under negative pressure, colder than ice and still liquid, so eager to remain whole that a single bubble would snap the column in an instant. Yet day after day the chain holds, linking soil to sky in an unbroken thread of molecules joined by hydrogen bonds tense as harp strings before the first note. Researchers place microphones on quiet branches and record minute pops, cavitations, when drought forces tension too far. The tree seals the wound, grows new xylem, and the thread resumes. It is water behaving like glass wire, strong yet invisible, humming inside trunks as if trees themselves were living barometers of atmospheric thirst. Thunders flash fried plasma. Clouds gather over a prairie, pile into anvil towers 15 kilometers high, then trade electric murmurs until one bold bolt rips sky to soil. For an instant, the channel of air and water vapor reaches temperatures hotter than the surface of the sun. Electrons tear free from oxygen and hydrogen atoms, forming a plasma, a fourth state of matter where nuclei drift in a sea of charged particles. The flash is over in thousandths of a second, but in that blink water has shown its capacity to host star-like fire, to step into a costume usually worn only in nebulae or fusion cores. In laboratories, scientists coax the same trick on a gentler scale. They pass pulses of radio waves through humid air, creating cold plasmas inside glass tubes that glow violet and clean surgical instruments without heat or bleach. Some dream of plasma-assisted combustion chambers where a mist of water vapor and air cracks into radicals that ignite diesel more completely, trimming soot to wisps. Others imagine plasma jets driven by microwaves that break carbon dioxide on Mars into oxygen and carbon monoxide while converting trace water ice into rocket fuel for a homebound craft. Each idea leans on water's willingness to escort charge across the frontier between dark and dazzling. High-pressure ice palaces drift now beneath Europa's frozen crust. A dark ocean pounds the underside of an ice shell 20 kilometers thick. Pressure there multiplies until familiar hexagonal ice 2 gives way to cubic ice 3, then to dense ice V, then to ice 6 where molecules stack in double cages, oxygen atoms pressed shoulder to shoulder. Deeper still, in the cores of giant planets, water may lock into ice 7 or ice X, structure so compact that hydrogen atoms sit equidistant between oxygens, sharing ownership in a quantum blur. These exotic crystals could float atop metallic oceans of superionic water, where protons roam freely like electrons in a metal lattice, making the layer both solid and conductive. Perhaps the source of Neptune's quirky magnetic field that spins off-center from its axis like a carnival ride. Scientists recreate slivers of these palaces in diamond anvil cells no larger than a ring box. They squeeze a speck of water between gem tips, flash heat it with lasers, and watch ruby sensors record pressures that would flatten Mount Everest into sand. Under such force, ice glows as it conducts electricity, hinting that planets might hide thermal circuits deeper than any miner's drill will reach. When the squeeze relaxes, the speck often snaps back to liquid, unfazed, as if extremes were only a passing dream. Glassy nightfall in interstellar space. Far from stars, grains of water vapor collide with cosmic dust cooled near absolute zero. At such chill the molecules land, stick, and freeze without time to arrange themselves. The result is amorphous ice, glassy and porous, a maze of hollows that traps neon, methane, perhaps even strands of organic precursors. Comets store this dusty snowball for eons. When one drifts sunward, sunlight warms the glass, ice rearranges itself into crystalline order, and trapped gases explode outward in flares that bloom into tails millions of kilometers long. Astronomers reading ultraviolet spectra of those tails decode the recipe of ancient molecular kitchens that predated planets. Somewhere in that recipe may lie clues to why early Earth erupted with life so quickly once oceans cooled. Closer to home, the James Webb Space Telescope stares at exoplanet atmospheres and catches fingerprints of water vapor swirling at temperatures too high for oceans, too low for full plasmas. These are worlds of hot ice clouds or steam jungles, entire climates balanced on the edge between liquid, vapor, and crystal, proving that water loves the liminal. Proton tunnels and quantum waltzes shrink the scene to a single bond deep inside a block of ice at minus 200 degrees Celsius. Classical intuition says nothing should move there. Atoms locked, vibrations stilled. Yet quantum mechanics offers a loophole. Protons in hydrogen bonds can tunnel, vanishing from one side of an energy barrier and reappearing on the other without crossing the space between. Experiments with neutron scattering show twin peaks in diffraction patterns, evidence that the proton occupies both sites at once, like a note played on two strings simultaneously. This tunneling matters in enzyme catalysis, in proton wires inside membranes, even in the slow aging of ice sheets, where tiny shifts ripple outward over millennia like echoes in stone cathedrals. Take a quiet breath, imagining that proton slip as a whisper across frozen halls. Exhale, knowing distance can be bridged in ways our common senses never reveal. Industrial shadows, water jets and shock tubes. Not all extremes hide in oceans and stars. Some roar on factory floors. High-pressure pumps squeeze ordinary tap water to 4,000 atmospheres, focus it through nozzles finer than a pin, and release a jet that slices stainless steel plate like paper. Add powdered garnet to the stream and airplane wings, armored glass, even granite slabs surrender in neat lines. The liquid exits as mist. All the cutting heat has been carried away by mass rather than flame, a practical display of water's paradoxical gentleness and force. In research tunnels called shock tubes, engineers blast a diaphragm apart to send a supersonic front through humid air, studying how water vapor condenses behind pressure waves in engine intakes or volcanic eruptions. Sensors record microsecond shifts, deciphering how droplets form and vanish faster than an eye can blink. Each datum helps design quieter jets, smarter rockets, safer mining detonations. When water remembers fire, beyond pressure and plasma lies another frontier. Supercooled flame. Chemists bubble flammable vapor through water until the liquid reaches temperatures below its typical flash point, then trigger localized combustion with lasers. Tiny fireballs bloom beneath the surface, baskets of ionized gas wrapped in a skin of vapor. They rise like balloons, flicker, and fade without boiling the bulk liquid. The phenomenon hints at reactors where burning can proceed in safer, cooler envelopes, turning biomass into fuels with fewer pollutants. Even in flame, water slips into moderate frenzy, holding reaction and rest in a single cupped palm. A gentle return. Let the parade of extremes slow. Supercritical tides fall quiet. Plasma channels fade to invisible ions. Diamond anvils release their grip. Glassy comets drift back into night. The droplet that began this journey resumes a familiar shimmer. Clear, cool, reflecting starlight on a palm. Yet it carries new weight in memory. An echo of thunder hotter than solar storms, a whisper of proton tunnels, a ghost of ice 7 lurking beneath alien seas. Draw a breath steady and full. Feel ribs expand like a submarine's ballast tanks rising from abyss to surface. Hold the breath in tender suspension, as if balancing between liquid and vapor. Release it slowly, letting each muscle soften the way supercritical water eases back into clarity when pressure subsides. The shoreline returns, waves padding across sand. They have traveled from cataracts under Antarctic ice, from equatorial storms, from deep vents lit by chemiluminescent worms. Extremes may mold water into forms as strange as dreams, yet each molecule can still find its way here, to this quiet beach, to your quiet breath. Rest in that certainty while night journeys on. Dream descent, into the still blue. The tide has slowed to a lazy hush, brushing sand as softly as a mother smoothing a child's hair. Let its rhythm become your own. Inhale as the wave approaches, pause as it meets the shore, exhale as it slips back into the dark. Each breath grows quieter than the last, like lanterns along a pier dimming one by one. Imagine the night sky tilting until stars pour toward the horizon, scattering across the sea like silver grains. With every exhale you drift among them, weightless, wrapped in a faint glow that pulses in time with your heartbeat. Thoughts loosen, floating free, then dissolve like salt in warm water. No effort, no hurry, only gentle release. A wide blue current appears beneath you, glass smooth and endlessly deep. Lower yourself onto its surface. It supports you without a ripple, cool and forgiving. The current begins to glide, carrying you past glimmering constellations mirrored below. Each reflection wavers, then settles, until sky and water merge into a single soft darkness. Far below, faint lights flare and fade, the last sparks of distant vents, the quiet flash of underwater storms. They feel remote, harmless, like memories you no longer need to hold. Let them sink out of sight. Above, clouds part to reveal the full moon, pale and round, its reflection a silver path leading farther into calm. Follow that path. Breathing is effortless now, rhythm slowed to a whisper. Muscles unwind. Eyelids grow gently heavy. The current narrows to a lagoon enclosed by night-blooming lilies whose petals close in silent greeting. They release a cool mist scented with rain on warm stone. In its embrace, even the smallest tension slips away. Drift deeper into stillness. Hear your pulse echo once, then fade into the hush beneath the water's skin. Feel your body cradle its own warmth, suspended between sky and sea. Thoughts fade to a dim shoreline far behind, replaced by a vast, tranquil blue where only dreaming remains. You are floating, breathing, dreaming. Nothing more is needed. Let the lagoon cradle you until the first light of dawn, soft and sure, arrives to lift you gently from the water's embrace. A whisper from the water. Thank you for joining Night Chemistry on this journey through water's hidden worlds. From candlelit laboratories to supercritical oceans, from proton dances to ice palaces beneath distant moons. May these stories settle in your mind like snowflakes on a quiet pond, cool and clear. As you drift toward sleep, remember, every breath you take returns molecules that once glimmered in comet tails, pulsed through ancient reefs, or cooled the furnaces of stars. Two small hydrogens, one generous oxygen. Simple, constant companions flowing through all life, linking your heartbeat to tides, to clouds, to the slow turning of the earth. Let that thought rest beside you through the night. When morning light finds your window, may you rise refreshed, carrying the calm of oceans and the quiet strength of a single droplet holding the history of the world. Sleep well, Voyager, and until next time, peaceful dreams and gentle tides.